Welcome to the deep dive. We spend so much time obsessing over the big, complex parts in engineering marvels. But today, we're going micro. We're drilling down, quite literally, into maybe the smallest, most overlooked component in high-performance mechanics, the humble fastener. We're talking screws, nuts, bolts. Specifically in the world of high-end RC models, think those amazing vintage Tamiya and Kyosho kits, every single screw counts.
Yeah, it's fascinating. You have builders spending, serious money on pristine chassis, rare electronics, perfect bodies, and then the parts actually holding it all together, the screws, they often treat them like cheap consumables. Buy them in a big bag, lowest price wins.
And that's exactly what we want to dig into today, that initial saving. It's textbook false economy. For anyone serious about RC, especially vintage restoration or racing, the real cost of cheap hardware isn't measured in pennies. It's measured in, frankly, permanent damage to parts you just can't replace, or maybe a catastrophic failure right when you need performance most.
And we're really looking at this through two lenses, right? Preservation and performance. If you're restoring, say, an old Tamiya Rough Rider, you're all about preservation. You need to protect that aged, brittle, irreplaceable plastic. If you're racing a modern buggy, it's about performance, unshakable mechanical reliability under serious stress. And interestingly, both paths lead to the same conclusion. You absolutely need top-quality, application-specific hardware.
Right. So today we're going to explore what happens when you play metallurgical roulette with cheap parts. We'll look at the strip dead epidemic. We've all been there. We'll tackle the specific puzzle of those vintage Japanese kits, and then lay out a kind of master builder's strategy for using the right fasteners.
Yeah, the goal here is really to elevate the fastener. It's not just a bit part. It's a critical engineered component. It contributes directly to your model's success, its longevity.
Okay, let's start with the dark side then. That big bag of generic screws from, wherever. They cost next to nothing. What are the immediate red flags? What goes wrong first?
The first, and honestly the biggest risk, is what you called material roulette. It's a great term. When you buy steel screws without a specific grade, well, steel can mean almost anything. These cheap fasteners use unspecified low-grade alloys. The result: wildly unpredictable, inconsistent material properties, sometimes within the same bag.
Wow, okay, so you're saying I could pull out one screw and it might be super soft, and the very next one could be brittle as glass.
Exactly. That inconsistency just kills any attempt at proper assembly. A soft screw, the threads might strip, or the head rounds out with hardly any torque. A brittle one, maybe bad heat treatment, maybe none at all. It snaps clean off under a shock load, or even just tightening it down. It turns assembly into a gamble.
That unpredictability sounds like a nightmare. And it's not just the metal itself, is it? The sources mention problems with how they're actually made, too.
Correct. You've got basic geometric flaws. Things like oversized diameters, threads that are poorly formed or even damaged right out of the bag, burrs. But the one that probably bites hobbyists most often, it's the hex socket. Cheap screws often have really sloppy hex tolerances.
Meaning the socket is just a tiny bit too big for a good quality driver.
Precisely. So instead of your driver engaging firmly on the flat faces of the hexagon, it only really makes contact with the corners, the weakest points.
Ah, I see. And if the metal's already soft, applying torque just to those corners?
You got it. It basically guarantees the head will deform, round out, boom. Project stop, you've got a stuck screw.
And this links back to what you mentioned earlier about systemic failure. How does one dodgy screw end up wrecking, say, a suspension arm?
Right, think about how these RC cars are designed. They rely on everything being clamped together tightly, securely. If one screw is out of spec, maybe oversized, maybe the threads are bad, and you can't tighten it properly, that joint stays a bit loose. When the car runs, especially off-road, that looseness allows tiny movements. We call it fretting.
Okay, like microvibration.
Exactly. And those vibrations transfer stress and friction to the adjacent screws, the ones that were initially tight. Over time, they start to work themselves loose too.
So the failure cascades. One cheap screw starts a chain reaction that loosens the whole area.
Yes. And that systemic loosening puts abnormal stress, accelerated fatigue on your high-value parts. Suddenly, that single 10-cent screw failure leads to a $50 carbon fiber arm cracking, or worse, shattering an irreplaceable vintage gearbox casing.
Ugh, the strip head epidemic. I think every single person who's ever wrenched on anything has hit this wall, that moment the driver just spins. What do you even do then? How do you get those things out without destroying the part around it?
It's awful, isn't it? It turns a simple task into this high-stakes, often destructive extraction. The usual methods are pretty brutal. You might have to carefully use a Dremel tool to cut a slot into the head for a flat blade screwdriver. One slip and you've gouged the vintage plastic, or the other desperate measure, gluing your hex driver into the stripped socket, often using super glue and baking soda as a kind of instant epoxy.
Gluing the driver in. Wow. That sounds less like a repair and more like, well, a last resort. One shot.
It really is, and the risk of damaging that pristine, maybe 40-year-old part, it just completely wipes out the couple of bucks you saved on the cheap screws in the first place.
That is the absolute definition of a false economy, isn't it? Low initial cost, potentially massive downstream cost and risk.
Couldn't say it better myself.
Okay, this is where things get really interesting, especially for listeners who are into restoring the classics. Those vintage models, particularly the Japanese gems from Tamiya and Kyosho in the 80s,
Yeah.
they have their own unique set of challenges, right? Due to their age and how they were originally made.
Absolutely. The number one thing, the thing that catches so many people out, is the JIS standard imperative. Those vintage Japanese kits didn't use the Phillips head screws we're all used to seeing. They used Japanese Industrial Standard, or JIS crosshead screws.
Hang on, they look almost identical. I mean, side by side, it's really hard to tell them apart. How different can they be?
That's the trap. They look similar, but the design philosophy is totally different, functionally different. A Phillips head driver is actually designed to cam out, to slip out of the screw head recess easily. This was originally done to prevent over-tightening on assembly lines. A JIS driver, however, has a recess with parallel sides. It's designed for maximum engagement to transmit higher torque without slipping or camming out.
Ah, okay. So if you take your standard household Phillips screwdriver to an original JIS screw,
You're essentially guaranteeing it will cam out prematurely, you won't get good engagement, you'll apply force badly, and you will damage the head of that original screw.
so using the wrong tool isn't just less effective, it's actively damaging if you're trying to preserve those original parts. And then you're forced to find replacements, where you might fall into the trap of using cheap, poor quality screws we just talked about.
It's a classic knowledge gap leading directly to physical damage. And then you layer on top of that the challenge of the materials themselves. We're talking about plastics from the 1980s, ABS, nylon, polycarbonate. Over decades, the polymer chains break down. They lose plasticizers. They become significantly more brittle.
Right, the part that felt tough and maybe a bit flexible when it was new is now much more fragile.
Exactly. So now imagine trying to force a replacement screw, maybe a cheap one that's just fractionally oversized, into one of those aged plastic parts. It acts like a wedge. The brittle plastic can't really yield or deform like new plastic would. Instead of cutting new threads cleanly, crack. It splits the plastic boss that little tower the screw goes into.
And that compromises the structure permanently. There's often no good way to repair that.
Pretty much. Which means for restoration work, you actually have to redefine what quality means for a fastener. Maximum strength isn't always the best thing.
That's counterintuitive.
It is. A modern, super strong, grade 12.9 screw might seem superior on paper, but if its manufacturing tolerances mean it's just a tiny bit too big for that 30-year-old hole, it's destructive. In that scenario, a dimensionally perfect, maybe slightly softer A2 stainless steel screw could be the far superior choice. The priority shifts to minimizing harm and preserving the integrity of that irreplaceable vintage part.
Okay, so cheap screws are bad for preservation, bad for performance. Let's talk solutions. What are the reliable, high-quality options? Let's start with the workhorse A2 stainless steel.
Right. A2, sometimes called 18-8 stainless, it's a very common, reliable grade. About 18% chromium, 8% nickel. Its main selling point isn't necessarily brute strength. It's rated around 700 megapascals, which is decent but not extreme. No, its real value is its excellent corrosion resistance. That's huge for any RC car that might see wet grass, puddles, or even just humid air. It solves that really common headache of rusty screws.
So you're consciously trading off maybe ultimate tensile strength for that everyday resilience and low maintenance.
Exactly. It's a solid, dependable choice for general use. And good suppliers, like Team KNK, for example, add value in other ways, too. Their kits often come pre-sorted, with specific sizes clearly labeled in separate compartments. That dramatically cuts down on human error. You're much less likely to grab a 12mm screw by mistake and try to force it into a 10mm hole, which, as we know, can crack plastic or strip threads.
Makes sense. Now moving up the scale. For peak performance, especially in racing, what are the premium choices? Let's talk titanium.
Grade 5 titanium, often designated 6AL4V. This is generally seen as the ultimate upgrade for racing. It's basically aerospace-grade stuff. It's incredibly light, very strong, and practically immune to corrosion. The key number here is weight. It's about 40 to 45% lighter than steel, but still boasts excellent strength around 950 MPa.
Okay, 40% lighter sounds impressive, but we're talking about tiny screws. Is that weight saving really noticeable? Does a 50-cent titanium screw actually make the car handle better than a 5-cent steel one, or is it more about bragging rights?
Oh, it's absolutely measurable, especially at competitive levels. It's not just about the total weight, it's about where you save that weight. You use titanium strategically to reduce unsprung mass. That's the weight of components not supported by the suspension wheels, hubs, axles, knuckles. Less unsprung mass allows the suspension to react much faster to bumps and track irregularities, keeping the tires in better contact with the surface, better traction. You also use it high up on the chassis mounting shock towers, for instance. Saving weight up high lowers the car's overall center of gravity. That directly improves stability and cornering speed, fractions of a second matter in racing.
Gotcha. Okay, that makes tactical sense, reducing unsprung mass and lowering the CG. Very cool. All right, finally, what if weight isn't the main concern, but you need absolute maximum strength, pure clamping force?
Then you're looking at grade 12.9 alloy steel. This is pretty much the pinnacle for metric fastener strength, rated around 12 and 20 MPa, significantly stronger than A2 stainless or even grade 5 titanium. You save this stuff for the really high-stress joints. Think motor mounts, where vibration and torque are intense. Transmission case halves that need to be clamped together rigidly. Suspension hinge pin mounts that see huge shear loads on impacts.
But looking at the comparisons, there's a big downside here, isn't there?
A massive one, corrosion resistance. Grade 12.9 alloy steel has basically none, that black oxide coating you see on them. It offers very minimal temporary protection. It wears off fast. If you run a car with 12.9 screws in damp conditions, or even just store it somewhere humid, you have to be diligent with maintenance. Regularly wiping them down with a light oil like WD-40 is essential, or rust is pretty much guaranteed.
Okay, so let's recap that comparison quickly. Grade 12.9, strongest by far, heaviest, very prone to rust. Titanium, lightest, still very strong, excellent corrosion resistance, but expensive. A2 stainless, good balance, excellent corrosion resistance, moderate strength, generally affordable. This really drives home the point. There's no single best fastener for everything.
Exactly. Which leads us to the smart approach, what we call the hybrid strategy. The master builder doesn't just pick one type, they mix and match.
All right, so how does that look in practice? If you were building, say, a high-performance buggy, where would you put each type?
You engineer it.
Huh.
For those critical high-stress joints we just talked about, motor mount, gearbox halves, inner suspension pivots, that's where you use the grade 12.9 alloy steel for maximum clamping force and shear resistance. You accept the maintenance requirement for the strength benefit.
Okay, and then for the general chassis stuff, the parts that hold the electronics tray, the main chassis plate, maybe bumpers?
That's prime territory for A2 stainless steel. It's plenty strong enough for those applications, and you get that crucial, hassle-free corrosion resistance. Set it and forget it, basically.
And the fancy grade 5 titanium.
You use that strategically for performance gains, shock towers, definitely, to lower the center of gravity, and wheel side components, things like screws holding on wheel hubs or steering knuckles to reduce that critical unsprung mass. It shows that choosing fasteners isn't just assembly, it's actually part of tuning the car's handling and performance.
Right, it's thinking like an engineer, not just a mechanic.
Yeah.
Now, one last crucial piece. Having the best hardware in the world is useless if your tools or your technique mess things up during installation. What are the must-do best practices here?
Number one, absolutely non-negotiable. Invest in high-quality tools. Precision ground tool steel hex drivers, like those from MIP or similar brands, their fit is exact, which minimizes the chance of stripping even good quality screws. And, as we discussed, if you're working on vintage Japanese kits, a dedicated JIS screwdriver set isn't optional. It's mandatory to avoid wrecking that original hardware.
Good tools make a huge difference. Okay, what about installation tips? Anything specific to prevent damage?
Two key things that can save you major headaches and potentially irreplaceable parts. First, when you're threading any screw into plastic, especially older, potentially brittle plastic, put a tiny dab of silicone grease or even just wax, like beeswax or paraffin wax, on the screw threads first. This lubricates the threads as they go in, drastically reducing friction and the stress on the plastic. It makes cracking those fragile screw bosses much, much less likely.
That sounds incredibly simple, but it could save a world of pain, especially on vintage builds.
It really does. It's a tiny step that prevents catastrophic failure. Second, for metal-to-metal joints, particularly screwing steel into aluminum, like motor mounts or bulkhead braces, use a thread-locking compound. Loctite blue, usually 242 or 243 is the standard. It prevents screws from vibrating loose over time, which is a common issue in RC. And the final technique point. Don't over-tighten, this is huge. Tighten screws until they feel snug, then give them just a tiny extra turn, maybe an eighth of a turn, no more. Let the quality of the hardware and the thread locker do their jobs. Brute force just leads to stripped threads or broken screws.
Wow. Okay, this has been a really illuminating deep dive into something most of us, myself included, probably don't think enough about. The conclusion seems crystal clear. Choosing high-quality application-specific fasteners isn't really an extra expense you can choose to skip. It's a fundamental investment in the reliability, the performance, and ultimately the longevity of your cherished RC vehicle.
Absolutely. And
Yeah.
maybe stepping back for a second, this whole discussion about the tiny details in a hobby model, it highlights how crucial understanding materials and using the right components is, even for the smallest parts. So it kind of leaves you, the listener, with a question, doesn't it? If the structural integrity of, say, a 30-year-old plastic RC car hinges on knowing the difference between JIS and Phillips, or using stainless versus alloy steel, what critical, maybe overlooked components are holding things together in your everyday life? Think about your car, your bike, maybe equipment at work, even things around your house. Are they relying on mystery metal from the lowest bidder? Are you potentially exposed to the risks of a false economy somewhere important just because the fasteners seem insignificant? What might you be overlooking?